Assalamu alaikum and very good evening to all of you. I hope you had a very good day today. In this video, I am going to explain various utility functions and demand functions, including Cobb-Douglas and constant elasticity of substitution function. Let me start with the Cobb-Douglas utility function. The Cobb-Douglas function is most widely used in consumer theory as well as in producer theory, and this function is given by u of xy such that x is raised to power alpha and y is raised to power beta. Uh, X is one good and y is another good, and alpha and beta are exponents of x and y. Where for convenience we assume that alpha plus beta are equal to 1, and by definition the Cobb-Douglas function accords to constant return to scale in production theory, and here it's alpha plus beta is equal to 1, just like we have constant return to scale in the producer theory. We can now solve for utility maximization. Value of x and y for any prices px and py and income m. So we suppose that the consumer has a fixed income m, price of x is given by px and price of y is given by py, and the consumer wants to maximize utility from the consumption of good x and y. In order to do that, we set the Lagrangian expression. Because this is constraint maximization, the consumer may maximize utility subject to the budget constraint. This is not unconstrained problem, but this is constraint maximization problem. So we set Lagrangian function like this. This L is equal to x raised to the power alpha, y raised to the power beta plus lambda, where lambda is the Lagrangian multiplier, and this is the budget equation, and that yields the first order conditions. So if you take partial derivative of this L with respect to x, we get this, and if we derive this partially with respect to y, we get this equation, and finally if we take the partial derivative of this L with respect to lambda, we get this equation, the budget equation. And if we solve these equations simultaneously, we get the optimal level of x and y. So the optimal value of x is given by alpha time m divided by price of x, and the value of m is equal to beta m divided by py. So both of these x star and y star are the Marshallian demand function, which are the direct function of income and inverse function of own price. So it means that if consumer income increases, the consumption of x will increase, and if price of x increases, the consumption of x will decrease. So this is opposite relationship, and same is the case with y star, which is a function of income and consumption of y varies very directly, and similarly price of y and consumption of y are inversely related. So if price of y increases, consumption of y will decrease. So these are Marshallian demand curves. So we know that the optimal levels of x and y are given by x star as before, and y star, where x star is alpha m divided by price of x, and y star is equal to beta m divided by py respectively. Now suppose that the price of x per unit is $1 and the price of y per unit is $4, and the consumer has a total income of $8. So if we substitute these values in these optimal levels of x and y, then we get, and we also suppose that alpha and beta both are equal to 0.5, so that this individual split their income equally between these two goods. Now the demand equations 2 and 3 imply that x star is equal to this and y star is equal to this, and if we plug in these values of px and py and m into these Marshallian demand function, then it means that the optimal level of x will be 4, the optimal level of y will be 1 if we simplify this, and at these optimal choices the utility will be finally equal to 2 if we put these values in it. So this is the utility maximum level of utility which the consumer can achieve subject to this budget constraint. We can also compute the value of the Lagrangian multiplier lambda associated with this income allocation by equation 1.1, and that is given by this equation. Lambda is equal to alpha times x raised to the power alpha minus 1 times y raised to the power beta divided by px, and if we substitute these numerical values from here in this equation, then finally we get that the value of lambda is equal to 0.25, since 1 raised to the power 0.5 is equal to 1. Now this value 0.25, the value of lambda which is equal to 0.25 implies that each small change in income will increase utility by approximately 1/4 of that amount. So suppose, for example, that this person had 1% more income, that is, income is now $8.08 instead of $8. In this case, she would choose x is equal to 4.04 and y is equal to 1.01, and utility would be 4.04 raised to the power 0.5 times 1.01 raised to the power 0.5, and finally we have utility 2.02. So hence a 0.08 increase in income increased utility by 0.02 as predicted by the fact that lambda is equal to 0.25. So this is how we can analyze utility maximization and computation of the Marshallian demand function for x and y given the consumer budget constraint. There is another important utility function that is known as CES, that is constant elasticity of substitution, and this function is given by u as a function of x1 x2 is equal to x1 raised to the power rho plus x2 raised to the power rho whole raised to the power 1 minus rho, where 0 is not equal to rho is less than 1, and this is known as the constant elasticity of substitution utility function. We can easily verify that this utility function also represents preferences that are strictly monotonic and strictly convex, and the utility, the indifference curves derived from this utility function will be convex to the origin, negatively sloped and non-intersecting. The consumer problem is to find a non-negative consumption bundle solving this problem, and the problem is to maximize x1 raised to the power rho plus x2 raised to the power rho whole raised to the power 1 divided by rho, and the consumer is consuming x1 and x2 units of x1 and x2 subject to the budget constraint. This p1 x1 plus p2 x2 minus y is less than or equal to 0. To solve this problem, we we set up the Lagrangian expression, and the Lagrangian function is set like this. If we solve the constraint maximization problem, it will yield the Marshallian demand functions for x1 and x2 as follows. So this is the Marshallian demand function for x2 good in case of the constant elasticity of substitution utility function. So this is the demand function for x2 commodity, and similarly if we want to solve for x1, we will substitute this into to get this is the into the budget function. If you substitute this value in the budget constraint, then this solves for x1, and the Marshallian demand curve for x1 is given by this function, that is p1 raised to the power 1 divided by rho minus 1 whole divided by p1 raised to the power rho divided by rho minus 1 plus p2 raised to the power rho divided by rho minus 1, and finally if we define the parameter R, which is equal to rho divided by rho minus 1, we can simplify x2 and x1, and we write the Marshallian demand function as x1 function of price factors and income, and that is given by this function. Similarly, the Marshallian demand function for x2 is given by this function. So in this video, I discussed the Cobb-Douglas utility function, and then we found the solution value of x1, x2, and the Lagrangian multiplier, and then we used the constant elasticity of substitution utility function, and we derived the Marshallian demand function for x1 and x2, and we showed that both the indifference curves in both cases are strictly convex to the origin, and they are non-intersecting, as well as they are negatively sloped. So there is a little bit difference between the Marshallian and Marshallian demand function in case of Cobb-Douglas and in case of CES. In case of Cobb-Douglas production function, the Marshallian demand function of x1 varies directly with the income and inversely with own price. But in case of the constant elasticity of substitution function, the Marshallian demand function for x1 not only depends on own price, but also on the other prices, as well as the income of the consumer. So this is the main difference between the constant elasticity of substitution utility function and the Cobb-Douglas utility function and the demand functions. So solution to the consumer problem is this, and they depend only on its parameters P1, P2 and Y. So it means that the Marshallian demand function in case of the constant elasticity of substitution function depend only on the parameters as well as the price of the two goods and the income. If there are n goods, then the Marshallian demand curve will depend upon the prices of n goods and the income of the consumer. So ladies and gentlemen, this is a very interesting analysis of the Marshallian demand curve in case of the Cobb-Douglas production function and in case of constant elasticity of substitution. If you like the video, kindly subscribe to the channel and don't forget to click on the bell icon so that you can get timely notification about my other videos that I'll upload for you. Thanks for watching this video, and kindly subscribe to the channel and share its various videos in various WhatsApp groups so that this could reach to maximum possible number of people. Thank you, and have a good night.